Hello, ladies and gentlemen. If you notice how kind of short this video is, I decided to break up this huge unit into smaller topic videos. So this first video will cover work and power. The following videos will cover energy and springs. So we break up this massive unit into three major topic divisions. And so we're going to start with work and energy, where we cover work in 2D, work on graphs, and power. And so we start with work, which is work equals force times distance. When you apply a force to an object and it moves a certain distance, then work is done. Where work is the product of force and distance, and the main criteria is that these two quantities have to be in the same direction. If the object moves horizontally, the force also has to be horizontally. Same thing applies vertically. If you apply a force vertically, then the object must move vertically as well in order for work to be done. So if an object is not moving, no work is done. If these two things are in different directions, also no work is done. And the unit for work is joules, which you can abbreviate with capital J. Okay, like all other types of energy. So work is essentially energy, the work to do something to make a change happen. All right. And so some of these problems may include work in horizontal direction and work in vertical direction. And when work is done vertically, you might notice something different where the force is equal to weight of the object. Because if you imagine lifting something up vertically, the force you're exerting is equal and opposite to its weight. Alright, so if you're moving an object up vertically, the force you're exerting is equal to its weight pulling downward. Alright, so these two things are equal to each other. Alright. Now, if it's moving horizontally, it's easy to see. Force and distance are quite easy to pick out. Now, what happens when you have work done in two dimensions, when you have work done in an angle? Okay, so again, the main criteria is that these two things must be in the same direction. If it's at an angle, it has both horizontal and vertical parts to it. So you have to use the component that matches the direction of the distance done. So if, for example, you have an object and it's being displaced horizontally and your force is being exerted at an angle, it's going to have both a horizontal component and a vertical component right here. So the one that's useful is the horizontal component right here. So we have to use that force in order to find the work done. And the way we do it is by using these vector component equations that are on your reference table. Since we are looking for the horizontal component, the horizontal component, we need to use this one, ax equals a cosine theta. Okay, it's essentially the same thing as any other work problem. It just involves that extra step of finding the component of the force and then plugging it right into the work equation. Okay, same thing applies if you're lifting something vertically. We have to use the vertical component, so that's sine. Alright, so keep in mind these equations are on the reference table. Just remember that the direction has to follow the force. So these two things have to be in the same direction. Now, the tricky topic here is work on a graph. And some people tend to forget this because this is rarely asked, but I'm definitely going to hammer this point home. And here we have a graph of force and distance. When they ask for work done, remember that work is force times distance. When we take our x value and multiply by our y value, we're going to get work, because force and distance are on x and y. Now, we got to remember we're taking the area under the graph. So that means we're going to take everything in this shaded region. For example, if they ask us what's the work done in the first 7 meters, we're going to take the area of this entire triangle right here, because our graph makes a triangle underneath the line. Now remember that triangle, the area of a triangle, is equal to 1/2 base times height. So in this example, our base is 7 meters times our height of 6 newtons. Okay, 7 times 6 is 42. 1/2 of that is 24 joules. Now, if, for example, they ask us in this funky interval of, let's say, from 3 to 5 meters, we need to break this up into shapes that we know. So here is a triangle and here's a rectangle. Take those two areas separately and then add them up to figure out what's the work done in that specific interval. So if I were going to show you the calculations here, we break it up into two shapes. We'll do the triangle first. The base here is from 3 to 5, so that's a base of 2 because we're going from 3 to 5. The height now starts at about 3 and it goes up to 5 as well. So that's 2. And we get 2 joules right here. Now the rectangle part is just base times height. We go from 3 to 5, that's 2. And our height is from 0 to 3. And we get 6 joules. And we add it all up for a total of 8 joules for that entire segment. So that's how you find work on a graph. If they ask for the most work done, then you find the graph with the biggest area highlighted, or if you look for the least work done, then you would have to look for the graph with the least shaded area. If they want it numerically, a value, then you have to resort to finding these calculations. If they just want least or most, you just look at the shaded area underneath the line. Okay? Then we have power. Power is the time rate of work or energy. How many joules are you expending per second? And that's measured as work over time. You could also expand work to equal force times distance and then put it over time. And then look here, distance over time is equal to velocity. So you can also get this variation of force times velocity. All of these things are equal to power. And this is also at the reference table. It also happens to be the bottommost equation on there on the back page. Okay? And the unit for power is watts. You could abbreviate it as capital W. Do not confuse it for work. Now, the relationship here is that if you spend more time doing a single job, you have less power. Versus if you take less time, then you do something really quickly, then you have more power. Imagine two people doing 10 push-ups. Person who takes their time has less power than someone who belts out 10 push-ups in less time. Okay? More work equals more power, so the more energy you expend, the more power you have. So it's all about energy per second. Now, sometimes you'll see on electric bills, okay? So they show you that you're spending money on kilowatts hour. Kilowatt hour. So what is this exactly? Kilowatt hour. So we know watts is a unit for power. And that time, hour, is measured in hours. You could have hours as a measurement of time. What happens when we get power times time? Now look here. Power times time will get you work. So this is essentially joules. Not exactly joules per se, but it gives you an equivalent for energy, which is joules. Okay, so power times time, kilowatt hour is a unit for energy. So it's joules, essentially. So equals work. So this is what you'll see on electric bills and like other power bills you see. Or something you spend on to get power into your house. And that's the end of this mini video on work and power. Stay tuned for the rest of the videos.